Alrighty, let's take a look at a little bit of a number trick. So what we're going to do is we're going to do this little trick here. I'm going to use a calculator to kind of go through the trick a little bit, but we're going to choose any number. Well, my favorite number is 14. It's just a number. So I'm going to take 14. I'm going to add 3 to the number, and then I'm going to hit equals to get the next thing. Now I'm going to double the answer, so I'll multiply by 2, get 34. I'm going to add 4 and get 38. I'm going to divide by 2, get 19. I'm going to take away the number that I started with, 14, and I get an answer of 5. All right, so we get answer of 5. If we do another number, now maybe you want to try one of these as you're watching here, maybe pause and just kind of follow along. But I'll do another number. I'm going to use the number 10, nice easy number to remember. Add 3, double it, and again, always hitting equals after each one. Add 4, divide by 2, minus the number, I get 5 every single time. Now, if you do it accurately, or you make sure to hit equals every time, you should always get 5 as your answer below it. Now let's use a little proof of it using algebra. Let's choose a number, n. Add 3 to the number, n plus 3. We double it, so we multiply that by 2, so it's 2n plus 6, because we have to make sure we multiply both sides by 2. We add 4, so we add 4 to the 6, so it makes it 10. Okay, remember, like terms. And we divide by 2, so we divide the 10 by 2, and we get 5. And then we take away the number we started with. So we had 2 n's, now we're down to 1 n. And it says through the proof that we get n plus 5, meaning that we should always get our original number plus 5. Well, that's different than what we solved inductively. This is deductive, this was inductive. So there must be some error in the way that we proved it, or some error in this proof. Now, some of you are keen in this case here, and some of you maybe can't quite see where it is, okay? Or maybe you just haven't been kind of adjusted to it. But let's go through the proof and see if we can find where the fallacy might be. Now, some of you might be yelling at the screen saying, Mr. Barkman, it's right there. Okay, you probably aren't yelling at the screen, but that's okay. We can kind of go through that. We will go through it together. Let's look at this here. Choose a number, n. Okay, so we're starting with a number. It's a variable. When we add 3 to that, we can't put these together, so that's good. Okay, n plus 3 is perfect. It's an expression. Multiply by 2, so we're going to multiply both pieces by 2. Add 4. Well, we can only add, when we add 4 to the whole thing, it just adds like terms, so 6 and 4 is 10. Divide by 2. Now, we divided the 10 by 2, but we forgot to divide the 2n by 2. So this is our error right here. Okay? What we should have done is divide this both by 2. And so the proof should have looked something like this. Okay? And I'm not going to write out the descripting. I'm just going to write out the proof here. So n plus 3, 2n plus 6, and 2n plus 10. That's what we should have gotten. Now when we divide these both by 2, 2 divided by 2 is 1, so this should be n, and this should be 5. So that's what we should have gotten right here. And when we take away the number we started with, take away n, we should just left with 5 as our final answer. And so that's where the fallacy is, meaning that we found what we should actually get. We should always get 5 as our final answer. Finding the fallacy, finding the error. Now it's algebraic, so we need to understand algebra as well and going through it. Okay, but finding the error will help us to come up with an accurate proof on our reasoning. And now remember, this is deductive. The way we did it to start, just trial, was inductive. So inductive, deductive.